Hi, everyone. Welcome to Patient-Focused Data Science at Takeda, Insights about Complex Disease States and Machine Learning. I'm Dan Hausman. I'm the Chief Technology Officer at a group within Deloitte Consulting called Converge Health by Deloitte. Our organization focuses mostly on working with patient data sets of various different types to obtain additional value to life sciences companies. I'm here with two people from Takeda who we've worked with quite a bit, involving in some of the projects we've been doing, and I'd like to let them introduce themselves.
Hi, everyone. I am Valerie Strizak, and I am an epidemiologist at Takeda.
And I'm Jennifer Dreyhaus. I'm part of the Global Outcomes Research team at Takeda, trained as a bench scientist and work as an epidemiologist with a lot of real-world evidence.
And we're going to talk today about work we've done in machine learning as well as deep learning, working within claims data sets to try and do useful functions for epidemiology, HUR, and other pieces of the life sciences value chain.
So at Takeda, we're a pharmaceutical company that has a long history of over 200 years. We've been patient-focused, innovation-driven global company that we primarily focus in unmet needs of oncology, gastroenterology, and neuroscience patients. I need the clicker. Thank you. So I'm a part of the HEOR team, the Health Economics and Outcomes Research team, and Valerie's part of the epidemiology team. And what we are tasked with is to conduct scientifically rigorous studies that identify the clinical, economic, and unmet patient needs. And the reason that we do this is that we would like to be able to understand what we should be targeting for patients, to prioritize what's important to patients, and to be able to communicate our product value and differentiate from those on the market. And we publish these studies to inform and communicate to payers the importance so that they reimburse for these medicines, the healthcare providers so that they can better treat the patients, as well as patients themselves. Internally, we use this data and evidence to make decisions in our research and development programs.
So what we're going to talk about is a project called DeepMiner. And as everyone knows here, it's quite fashionable, at least was in late 2017, to put the word deep in front of something and turn it into a cool new product that was differentiated from the old version of what we call miner. But the basic idea and hypothesis behind some of the work we were doing with DeepMiner was that there was a lot of, and still is, a lot of hype about what can be done with deep learning that's come out, such as convolutional neural networks, recurrent neural networks, these different tools that are seemingly quite magical in terms of what they might be able to do, but to really apply them in the space of, I'm going to have to fix this, in the space of actual epidemiology and health outcomes research. And there's a reality to this that it's not so easy to just apply these to medical data. And while there's lots of hope that we can just turn on these tools, we wanted to run a number of experiments, which we did in 2018, working with clients like Takeda. We worked with two other life sciences clients to run very specific analytical studies to work out methods that could be proof that we can use these tools, where we can use these tools, and what would need to be done to be able to scale up use of those tools. And so the work at Takeda in particular was using the AWS framework to be able to pilot out various different machine learning approaches to basically deal with this hypothesis that if we just threw tons of information into these machine learning models, they'd perform as well or better or more efficiently than if we used the traditional techniques of having a bunch of experts very carefully construct scientific analysis plans and execute them. And so we started off with a hypothesis, and this journey here for the past year or so has been to try and validate that hypothesis. And the team from Takeda here is here to tell us a little bit about the positives and some of the challenges we faced and how I think we have to overcome them as we go forwards when we do this kind of work.
Now, another great buzzword in the field is real-world data and real-world evidence. I just wanted to briefly talk about what those were and make sure we're on the same page. So when I talk about real-world data, I'm just talking about data that exists all around us, that's collected in sort of routine ways from wearable devices or your electronic medical records, disease registries, and things of that nature. And the evidence, real-world evidence itself, is really clinical evidence that we can glean from analyzing this data. Now, I use real-world data in a variety of ways, and I use it across the life cycle of research and development to address a lot of different types of questions. In the preclinical stage, I'm using this kind of data to understand the natural history of disease and the etiology of disease. Why are certain people getting sick? In sort of later stages, I'm using this data to better understand and the patient unmet need in these diseases, determined what their healthcare utilization looks like. And this follows all the way through the life cycle management into the end stages where that drug's already on the market, and it tells us about how that drug is performing. And this is really important to us at Takeda and to other pharmaceutical companies in our commitment to patients. It allows us to prioritize what drug targets we should be going after. It helps us better understand the safety and efficacy of our drugs in the real world. Now, specifically for this set of this project and a lot of other types of projects of this nature that I've conducted, we're using claims data. A lot of you probably know what claims data is, but it's the administrative data that is generated when you go and have any encounter with a healthcare provider, be it at with a physician or a hospital. And this data is not produced for epidemiology studies. It's produced to bill your insurance. And it's coded in a particular way using a coding system called ICD-9 or 10. And this data really has a very rich patient-level insight to what's happening to patients. It has their diagnoses, their procedures, the prescription medications that they filled. In other types of data, you have the ones that they didn't fill, which is also interesting, as well as the labs that are ordered.
So in particular, we used TrueVid and market scan data, TrueVid market scan and Optum data. And you can see about the scale of this data set is a 10-year set of records. We get up to, in some of the categories of content, around a billion facts for conditions. So if you were to look at the size of this data set on a disk, it's somewhere between 2 terabytes and 10 terabytes for one of these data sets. It's probably mid-level big data, but certainly not the big data that we'd be looking at if we got into electronic medical records, imaging data, genomic records. And one of the reasons why we really wanted to focus on the claims data is because it is probably the most well-understood and the most researched type of data set because it's been around longer than any of the other data sets. And we do have the long-term hope of using machine learning in these complex data sets that actually add a lot of dimensionality to what we're looking at. But we decided if we couldn't do this within claims data where there's a lot of expertise, we'd have a lot more exploring to do when we looked at other data sets. You can see here there's this reference to OMOP. If you can imagine, medical data is pretty complex in terms of the number of different concepts you might look at. A given diagnosis could be thousands of different entries in a field called diagnosis in a code. What OMOP allows us to do is get a standardized common data model as well as a common lexical model for this information. And the hope in both building out this DeepMiner framework and in general for doing things in real-world evidence to use a tool like OMOP is that when we build methods, we don't have to rebuild the method tied to the data source. we can tie the method back to OMOP and then be able to reuse it with a number of different data sources. Like in this case, we have 2 different claims providers who both provide their data in different formats.
So we're using this data and these analytic tools to better understand real-world problems. Specifically, the one that we're going to dive deep into today is treatment-resistant depression. Depression is extremely common in the United States. More than 16 million people will have had at least one episode of major depressive disorder. There's also a very large subset of people with depression that don't respond to the typical therapies. More than 30%, it's thought. And this is really devastating. The patients are often unable to participate in sort of their daily activities, are unable to work. And we have some quotes here from patients. I'm crying. My husband took off work again because I am crying and cannot stop. I've been crying for 2 days. And this really underscores the importance of coming up with ways to better treat these patients. And this particular problem is very challenging to tackle. We wanted to better understand treatment switching. Those with treatment-resistant depression are switching their medications, are often switching their medications frequently, or a medication stops working and they need to do a switch. And this is helpful for us to better understand because we may be able to get that patient to the right medication faster. If we understand why patients are switching, we can come up with ways to predict which patients are at the highest risk of switching. And part of this challenge is that the patient journey is very descriptive in nature. We can see the switching patterns, but we don't always know the context. So within the claims data and using the claims data, we can see what is associated with the cases that have treatment-resistant depression compared to those that don't. Now, the general approach that we've taken, a lot of it is the same to the standard epidemiology 101 that I would typically do. In the first sort of phases, I identify a diagnosis of interest. In this case, it's treatment-resistant depression. And then I define my cases with treatment-resistant depression and the controls, those without. And so that's, for this project, a very standard, typical method. Now, where this really differs is in this set. So typically, I need to upfront design it so that I look at specific predictors. So I need to know which things I want to look at. Using the machine learning approach, the computer can use all of the variables, and you don't need to, well, the hope is that you don't need to tell it anything really, that you can put the data in and out comes the results. So I would typically need to talk with experts and clinicians in the field and get their opinion. And so that's not very scalable, and it's very time consuming. You just don't know what you don't know. And the last part is also a very normal standard approach that I would do in any type of analysis of this sort, which is I then evaluate the model, I look for further analyses, and I have a readout of the results in, say, a forum like this. Now, specifically for this study, this is our general framework for the study design. We had one experiment we were looking at switching between medications. So perhaps having Lexapro and then switching to Zymbalta or something of that nature. The other experiment was switching within a class of SSRIs. So within the same class switching. So it was 2 different kind of lenses to look at patterns of why people switch. And then I have the case selection and control selection here in kind of a generic way. Our cases had to have at least one switch and have depression, and our controls had to have depression but no switches. And I'll talk about the matching component a little bit later.
So So as I said before, we put all of these data sets into this OMOP CDM model. And we decided to make sure we were not just shifting straight into using deep learning models, despite it would be very exciting to use neural networks. There's plenty of great modeling techniques to be able to look at this data that have better transparency, better explainability than that. So we worked to do both of these. And the basic approach was we started with tools like linear regression and random forest classifiers. And then we moved forwards, and I'll get into a little more detail about the more complex models we worked with. We are at the AWS reInvent, so here's a slide to give you some idea of what the physical architecture, at least the virtual architecture, looks like. We were working inside of Takeda's VPC, so everything had to be done in a controlled environment. There's a lot of constraints on using this kind of data, both from the groups that license the data as well as the teams that are giving access. So everything had to be done in that VPC. There was data sets that were sitting inside of Cloudera, as well as data sets that were extracted out of the data lake into an EBS store. And we had to pull all of those through using Python. And you can see we're using PySpark and Spark to sort of build scalable jobs. And some of the biggest jobs to do this kind of work actually is to do the reduction from those big 5 to 10 terabyte data sets down into these case control sets. And so there's this first workload of being able to run those queries, keeping in mind that we have complex queries relating to index dates and relative information that's not just a simple and or to pull those data sets. But that really can be done completely asynchronously from all of the machine learning work, because once we've built the case control type model, we can pull it across into what we show here as this deep miner environment. And this is a simple way of looking at it, which is we pull out feature vectors using Python to bring it into that environment. So the feature vectors, we'll talk about how we structured them. And then the linear models, we'd use standard CPU-based infrastructure to do scikit-learn to run those different models. For the deep learning, we use TensorFlow. And then all of those outputs would be pushed into storage and then reviewed within a combination of Jupyter notebooks, TensorFlow, and Python itself. And you'll see later that this is not a pure linear process, because as we go forwards, we often have to go all the way back to the original source to change the case control logic, because we're going to just sort of determine things that didn't work out perfectly in how we originally designed things that come out of the machine learning we work on. This is sort of a best practice view of what to do with 10.6 million patient lives to give you some feel for the kind of infrastructure we're talking about. Certainly you can scale up these clusters if you want things to run faster, or you end up working with much larger, more complex data sets. We've worked both in terms of using on-demand as well as spot pricing. Certainly, if we get to more complex models like these RNNs and LSTMs, they can burn a lot of cycle time doing the training on big data sets, at which point we might want to schedule with spot pricing to keep the price down. But we're mostly talking about models for what we did here that could basically train in half a day. So we could start the training in the morning and be able to get our evaluation results somewhere in the afternoon or maybe later in the day, and then be able to go back and look at how we wanted to move forwards for additional experiments the next day. And we were running maybe 10 to 30 cycles before we were done and said, well, we've gotten enough from this experiment, let's move on to something else. But to give you a feel for how do these feature vectors get created, let's start with the Cdm Data Model. And the Cdm Data Model, if you looked at all of the possible features, has about 56 million features. That means for all the different diagnosis, all the different code sets, you could have that much. If you actually look in the data itself, you find that most of that is never populated between ICD-10 and ICD-9 and all the CPT codes. So we end up with like the actual data set down to about 28,000 features. And so we built a feature vector of those 28,000 features by basically building a bag of concepts. And so to think about the bag of concepts, it's one long vector, and in it we have true or false readings for that individual patient for the time horizon we're looking at. Because keep in mind, if we're trying to predict the future, including the future can create a bit of a problem. And so we have up to the time horizon from whatever index or set date we want to look at in there. We've populated a mark for true or false, or we'll populate a total score of the number of times that occurred within that data set. And that's the input to the machine learning models we're going to use. It gets a little more complex with looking at temporal vectors. But really what we end up doing to build a sequence is we take that same 28,000 feature vector, and we repeat it over time. And the question you end up asking here is, well, what time horizon are we going to split the data? Is this a day? Is this a week? Is this a month? Is it a year? And that becomes some of the complexity of moving into some of the more sophisticated models, because how we build the feature vector is definitely going to impact how strong our capacity is for building predictive models on it. We did find, because the deep learning models, we'll get to them in a while, had a lot more consumption of resources, and at times they wouldn't even converge, that we could get benefit at times for using the following design pattern, which was we would build a feature vector using these linear models, which would include all 28,000 features. But the truth was, much like we reduced a feature to what data was populated, we could look in that data set and then say, well, which of these features in a linear model actually is a driver of predictive power? And pick at whatever scale we wanted to, those to enter into the ones we were going to look at a temporal vector. And that helped us to be able to reduce the complexity, because we are continuing to anticipate this complexity to explode out as we move beyond claims data. So we need some way of keeping that feature space small enough so we can put it into these more sophisticated modeling tools so they don't train and burn CPU that's really not generating any additional predictive power. We followed a pretty standard machine learning approach. We basically created a test set. In this case, we did a 90% of the total population and then a 10% holdout in order to doing the training to test. We wrote all of that as sort of the extracts we were running. There's certainly no special logic other than just holding out a certain random population for the test set, and that's what we use to do the evaluation of the models. We learned a lot, though, because as we went through this, not everything went as planned, and I think the Takeda team can tell a little bit about that.
So, one of the things that we were hoping to get out of this project was to test the assertion that we could give the data to the machine, and the machine would give us the results, and we'd have called it a day. But we learned pretty quickly that I still have a job to do as an epidemiologist. So one of the sort of not great results that we got, there was some top features that were popping out that seemed a little bit strange. And this occurred because we sort of figured it out, reverse engineered what was going on here. But with the Laszlo classifiers and the random forest models, we were asking the machine to pick out the top features that contributed to a switch. And what we found was that the cases were defined in that they needed to have at least one or more switches, and the controls didn't have switches. Well, one of the things that increases your probability of a switch is how long you've been on antidepressant medications. So therefore, our cases ended up being older than our controls because we didn't do anything to overcome that. And so some of the features that came out were diseases that differentially affect the old. So a top feature that you can see here is that pneumonia was an indicator that someone was going to have a treatment switch. Now, the way to address this is a pretty classic epidemiology method, which is to do some matching between the cases and controls. And in this case, we matched based on age, gender, and time censoring so that we could overcome that sort of imbalance. And so we used KNN, which is a machine learning method for this, which is kind of ironic because we were using a machine learning method to overcome a machine learning problem. And the diagram on the left is showing the distribution of age between our cases and controls at the beginning. You can see there's a large discrepancy in that age distribution, with the cases being on average much older. And then after matching, it's not perfect, but it's very, very close. The age distribution looks similar.
And we also came across another problem as we got our initial results. And as Jen described earlier, we started out with having to define our cases. And we wanted to look at people who had major depressive disorder. So boom, we have our case definition. And as you can see from this diagram, you start with that and everything else flows after. However, the machines will do what you tell them to do. We told them to look at major depressive disorder, and that's exactly what they did. The problem is that when the lasso classifier and the random forest models went to pick out the features, they started picking up synonyms. So you can see that there was dysthymic disorder as a major feature, and that is basically a synonym for major depressive disorder, and that was not terribly helpful.
And more so than that, it's not just major depressive disorder, but treatment-resistant depression itself. So you would often get both of those things. So the model, the machine cheated.
I think the positive of the machine cheating and the way we're referring to it here is that, back to our hypothesis that we can get aided by using a machine learning method. You might not have seen this if you didn't use an approach that was looking at every single feature. And while it makes more work that we have to iteratively cycle through, and when we find synonyms we didn't think of in our mind or didn't find from the epidemiologists, it gives us an early iterative agile cycle we can run through in QCing the first result to then pick out through machine learning what features we have to add to the case control definitions so that when we then run the actual experiment later, we have a much better managed analysis plan.
And so here our solution was to expand the case definition and to include the synonyms for treatment for major depressive disorder. And this made our definition much more exhaustive. The only caveat here is that we need to remember that we have now changed our research question, and we need to keep this in mind as we look at our results. All right, now we're going to start getting into some of the findings that we had from running these models. And the first finding was that you need an awful lot of information to really get the relative importance of features that predict switching. And what we found here, which was not surprising, is that something that is not very common but happens to be found mainly among people who do or do not switch ends up looking like a strong predictive feature. But it's really only for those people. And when you have lots and lots of data, you can actually start to parse out which are the features that were important across the population, which is what's really helpful at scale looking at drug development and treatment.
You can also see that we ended up pulling down from like 38,000 or 6,000 features that were in the data sets, a pretty small number, 24 to 109, due to the fact that we maybe would have needed more data if we wanted to pull out the ones that were rare. And certainly, if we're going to try and use this in any kind of report, it's not that useful to a physician to know about a feature that occurs 1 in a million times is highly predictive of a switch, because it's not going to come out to be something that you can actually apply in practice. So there's some real sort of scientific logic that has to be applied to the machine learning to see if it's practical knowledge or even knowledge we already have.
And we did find that both data sets aligned against the key features, which is great. That was very reassuring. But we did know going into it that Truven and Optum have slightly different features. Specifically, Optum has more procedure and lab-based data. And so we could find this in the feature lists of the two, such that you can see under Optum there are lab tests for cholesterol that pop up, whereas in Truven you can see that high cholesterol pops up as a key feature. And it was reassuring to see that they conceptually did line up, but that these different aspects of the data sets did show through as we did these analyses. And we did find that our top features mainly fell into 3 buckets, and that was great. It gave us a lot of face validity for what we were doing. So in the first bucket, you can see that features associated with going to see the doctor, such as having acute infection, that could be associated with a treatment switch. And you could see that makes sense because you need to actually be getting medical care to have a treatment switch, and you may be going for a reason unrelated to depression, but actually going to the doctor is a time that you can have a treatment switch. In the middle, we found that factors associated with unrelieved symptoms of depression, such as fatigue, were associated with a treatment switch. And again, this makes sense. If the treatment that you're receiving is not helping, then you may consider moving to a new one. And the final bucket looked at factors that are side effects of treatment, such as acid reflux. And again, that makes sense that if the treatment you're taking is giving you negative side effects, you may not want to continue on that same one. So again, this was helpful because it let us see that the features did line up, but there are fairly long lists, and when we have our medical experts are looking at the literature, it's hard to come up with as big a list of features that you are as confident in. And here we can also see that we found factors that were associated with switching, and they may be predictive of switching or predictive of remaining on the same treatment. But we can also see in this box that factors that are associated with not switching, they may not be very intuitive, and we realized that the criteria were not remaining on a particular treatment, but not switching to a different treatment. And so as we were thinking about this, we realized that we may be identifying people who did not continue taking their original treatment. And some of these, there were a lot of cardiac events. Realized that may be that they didn't switch because they stopped taking antidepressant medication overall.
So, we did want to compare, that was the ultimate assumption was these deep learning models would perform better than the linear models. And keep in mind, it's going to be hard to go and look at all of the features that were driving those models because they're not transparent in terms of explaining which feature drove which function. In our early experiments, I didn't put them on the graph. We tested out basically positioning convolutional neural networks as a way to look at those feature vectors. That didn't generate a ton of additional gain in terms of higher accuracy scores. What we did see in this, and keep in mind that this is one of about 7 or 8 experiments we ran, and so across all the experiments, we tended to see the same trend, that we could get improved performance somewhere on the order of 3 to 12% when we shifted to recurrent neural networks or LSTM type models. And in this particular experiment, it wasn't that pronounced. And I think one of the reasons why it wasn't that pronounced in this experiment is we weren't dealing with a huge predictive power. And if you look at these numbers, we're in the 50s, not the 90s. And something you'll have to just admit and accept in medical data, especially claims data, is you may not be able to get to those 90% predictive models because the data doesn't support knowing everything about the switch. And so we certainly know that we have to add more information if we want to predict these things, and it may even be possible that treatment switches aren't inherently predictable. We don't know, right? We can only know if we add enough data. But the big takeaway with the improved performance of the RNN and LSTMs is that we do believe, based on this and other experiments, that attaching a temporal model on top of these sort of non-temporal models gives the machine additional capacity to be able to do predictions that are going to be meaningful. The gap, and we'll talk a little bit about it later, is how do we take advantage of that going forwards? And maybe a second note is it's a little harder for us to keep track and manage the scorecard in these other models because unlike linear models, they don't have a necessary predicted endpoint. We run at a random starting point. They run over a course of time to generate the output of the neural network. And we'll end up with different networks depending on how we ran the model. And so we did run at different time intervals. And we found that at certain time intervals, we were getting high predictive power. But we think it's a good likelihood that within our test and training set, some of those time intervals created some overfitting. Because when we then changed the time intervals, they condensed to being only a slight gain. So you have to be kind of careful when you're dealing with the deep learning models, especially because you may not have the transparency to see exactly what's going on like we did with the linear models. So the big takeaway here is that we did see some of those benefits of being able to take a lot of different features and be able to bring them down to be able to highlight the ones of interest. We now do have a model to be able to do with drug switches. It doesn't just need to be working on MDD and treatment switches in psychiatry, which may be more complicated than some of the other things we may track. And we did see some improvement in the RNNs and the LSTMs that may be more capable long-term to produce the kind of results we might need to get a boost from the data that we have.
All right, and now we're going to just give you a brief overview of another case study that we did. And here we're looking at non-alcoholic steatohepatitis. And this is a condition that's becoming quite common in the US and worldwide, largely due to its association with obesity and metabolic syndrome. So here in the US, this affects about 9 to 18 million people. And up to 16% of liver transplants in the US are associated with NASH. And even more concerning, it's predicted that by 2020, NASH will be ahead of hepatitis C as the leading cause of liver transplant. The average patient here is middle-aged and has other factors such as obesity, high blood pressure, high cholesterol, type 2 diabetes. And these patients are often unable to work due to their health concerns, and they're also quite concerned about their NASH progressing to liver cancer. So here we did an experiment that was similar to what we did for treatment-resistant depression, but what we were looking for is factors that predict developing NASH. And again, we did 2 experiments. The first one looked at people who had NASH and compared them to people who did not have either NASH or its precursor, non-alcoholic fatty liver disease. And the second experiment looked among people who had NAFLD, and the cases were those who progressed and the controls were those who did not. And here our findings, on the medical side, our findings were that the factors that predicted development of NASH were either associated with findings such as esophageal bleeding that would prompt the medical provider to diagnose someone with NASH, or things such as sleep apnea that are associated with all of the comorbidities. We did find here that we were dealing with a much smaller number of people than we were in treatment-resistant depression, which is what's not surprising. We know it's a smaller population. But despite that, we actually had reasonable accuracy. And we also had some of the same problems that we encountered while looking at the major depressive disorder, which I can share with you.
My favorite hiccup in this project was that the strongest predictor for not developing NASH was death. So that was a fun finding where if you died, you couldn't get NASH. That was reassuring. And it also, the flip side of that is that NASH patients are immortal. So maybe it's not so bad to get NASH, I don't know. But we had to do a lot of the same kind of approaches where we're looking at matching and we're looking at how much time we're giving the cases and controls. And we really need to have that time censoring to be the same. The original study design had NASH patients could contribute data up until their NASH diagnosis, and the controls could give data over their entire lifespan. So the controls could die and the NASH cases couldn't. And I just want to highlight that that's when I was asked to join the team to work on this project. So the machines, and the take home also is that the machine learning still needs human input.
And I think you'll see here that we had quite a good gain in terms of using the LSTM and the sort of more temporal models. And I think part of that gain came from we have a higher predictive value to the original data set itself. And we're starting with being able to predict at the range of 65 to 75%, and we can boost that in various different ways within the different data sets. So it's still more positive feedback that the more we go into this neural network realm, we're going to be able to find new things that can be highly predictive and maybe build models that can be useful in ways we can't with the linear models. Where do we go from here? So, I said we don't know what sequences. So if you can imagine, we have a way now of maybe building these temporal models. We don't yet have a way of figuring out which sequences are driving those models. And so one of the areas we're doing work in is to build out GAN-type frameworks to be able to run random sequences back through our models once we know what they're going to predict, to see which of those sequences has the highest highlight on the model. Because until we can give explainable results back to Jen and Val and the scientific community of why these things are predictive, we really haven't accomplished much. Unless we're going to use it in some kind of decision support tool where you press a button and it says this person's going to get NASH. And so we really do have to put the time and energy in to start looking at these different techniques that can use more advanced machine learning just to even understand what's inside of our neural networks. And so we're also looking out at different techniques that are on the horizon to help us to get some transparency into these temporal models. Another area we're looking into is on some other projects we've seen things like vector embedding, which are another approach for us to be able to get a solution to some of the sort of idiosyncrasies to the data, can allow us to condense a lot of those features into combined features. So you can imagine by vector embedding, we can take 35 concepts that are all similar to, say, a visit to the doctor, but a very specific kind of visit to the doctor, and turn them into a condensed feature. We can use that then to feed into the models to get improvements to our scores, and then look at what are those vector embedded elements actually going to mean. And so we're still continuing to work on the modeling techniques on the back end to get higher utility for the scientists. I'd say the big lessons learned here is that we couldn't actually just drop all the data into a predictive model like we were hoping and end up being able to get what we wanted. But we could do it if we worked really closely with the scientific groups that were able to ascertain where the gaps. And I think more importantly, now that we know where most of the pitfalls are, it's a bit of a joke, I guess, that we've been through the random forest of sort of how to go through the journey. We can now design these much faster and be able to package these up into tools that can be reused on very many different disease conditions without having to worry about where we might go afoul. And that means now we're working on scaling up the models to be able to build up common analytic plans inside of our Deloitte group, and also working with the Takeda folks. We're building packages that can be run as standard packages that do all of these. That's a lot of the work we've done to extend our Miner platform with DeepMiner, but also the teams are given all of these tools because they're in Python notebooks, or we're working towards integrating SageMaker as a way to scale up some of these mechanisms, as well as working towards applying these outwards into other data sets. So, one of the things that Takeda has access, and I think 7 or 8 other pharma companies have access to, is a data set called the UK Biobank, which now extends from a pretty long patient record, but also has genomic data and imaging data. And so we have to start looking at how can we take these methods into new domains of information. Do you have another point? Go ahead.
No, I thought we were moving on.
Okay, yeah, sure.
It's so dovetailing on what Dan said by cutting him off. So where we are today is, from an epidemiology perspective within these groups at Takeda, we still have to cherry pick our predictors. We still have to tell our model beforehand what to look at. And that leads to an endless iteration of finding the right variables. And at the end of the day, we don't know what we don't know. The hope in the future for this is that the machine can use all of the available data. It can use thousands of covariates if necessary, and it allows a better understanding of patient outcomes. It allows a better understanding of that patient journey, and hopefully can uncover things that we didn't think of beforehand. It's also much more scalable. If we can get these models up and running, it'll take less man hours to get to findings, and then use that extra time saved on other priorities. So I think this was overall a very successful first look at using the machine learning.
So I think we should probably just move into questions. I'm trying to figure out how much time we have, because we have like 42 seconds before we hit that 15-minute time horizon. So I'd say we should open it up now to maybe talk about either any questions that came about from what we presented, as well as any thoughts others have about the future of this space. The microphone is over there, and so anyone who wants to ask a question is welcome to walk up to the mic, and we'll be happy to answer your questions.
question regarding the accuracy level. If I understood you correctly, you said like something like 80% range is your ability to predict. Is that correct?
What was your question?
Ability to use your model and predict, right, what the the risk factor is and so on. Your accuracy level is 80%. Is that correct? Did I understand you correctly?
I mean, we don't have a threshold for how predictive the model is. So I don't think that's fair to sort of push. Although we do want, in an ideal world, we have a 97% predictive power, right? Or something like it. Mm-hmm. But I think what's more important is that we can translate it back into supporting publications that would go out from the evidence management group. And so if there are findings that can then be validated against other data sets, or even within the data set can be validated as useful clinical drivers, we just need to then tie them back to some real statistical meaning once we bring those up, and maybe cluster some together to say, these set of factors are something you should be looking at in practice, or that a patient should be worried about.
Understood. Thanks.
Hello. I have a question about your platform. So for epidemiology, there are several platforms, commercially available platforms available.
Can you speak a little closer into the mic?
Sorry?
Thank you.
Okay. So there are several commercially available epidemiology platforms available. So I wonder why you do a homegrown solution with Amazon versus buy a turnkey solution or almost turnkey solution. What's your thoughts on that?
My use of the turnkey solutions is that the back-end technology is still logistic regression, and I still have to put in predictors. I haven't used a machine learning plug and play sort of model. So I think, like, at least from my standpoint, the turnkey platforms that I use, I still need to be able to still do that, the expert input needed to look at a list of predictors, whereas with the machine learning, the machine is telling me the predictors.
And I can also say in our experience working with a lot of different pharma companies, the dominant package model is SaaS. It's not some tool that's already built all of the pipelines and pieces. And sometimes groups are deploying packaged models that are basically development tools, but they don't have built into them necessarily all of the frameworks. And so there's still a gap, I think, out there for models, other than maybe there's a couple safety tools that are very specific for the methods that they use, that in most life sciences teams, they're still using a lot of coding in SAS and R, and maybe coding in Python to do the work they do day to day.
So you think your homegrown tools give you more flexibility versus the commercial tools?
Well, I'll let them answer to some degree.
Do offer
right?
the flexibility, for example, using R and Python. So I'm not questioning your decision. I just want to know the reasoning from you guys.
Absolutely. So in some ways, this was a proof of concept. Can we take their tools and put it on top of our data hub, and can it tell us something that's different? What we found in this is a lot of the project was about refining and getting the sort of steps and model correct, which we then now can move on and scale. At this point, we still have some refining to do. We didn't find any aha moments, but it has a potential to that, and that can be really important, especially where we have less content knowledge, where we don't understand the etiology of disease, we don't understand certain aspects of that patient journey. And so the hope is that this is one way that we can get at that the standard models and the platforms, the turnkey models that are out there right now, wouldn't be able to do. That's really a hope, and it's nice to be able to apply this new technology and try to adapt it and refine it to a tool that I can use in my daily work.
I'd also argue like the strategy from Deloitte is, we end up wanting to scale things that work, into packages that many clients can use, and we'll call that a product, whether it's an accelerator or it's something we're really going to support at Deloitte. And so we do these kinds of initiatives to build up all those methods so that we then have confidence when we try and scale it in multiple groups, that we're not doing 100 experiments all at once, learning for the first time. And so, the work we've done inside of Deloitte is to basically marry this pipeline or set of pipelines, which is the deep miner pipelines, into this capability we have that's done another piece of the workload that most of our clients struggle with, which is building cohorts. And so we're trying to pipe from build the cohort, those case control sets or just a large case population, to now have something on the backside that we can use to process it and run these. And so at this point, we have a version of this we can run turnkey with push buttons against all these methods. But we also see that most client teams we work with don't want a very rigid push button black box. And so we still have to leave a very open framework for editing the Python notebooks, editing the underlying code, especially because the technology is changing every day anyways for what can be done either on the scalability side or on what new machine learning tools we have to work with.
Okay, my last question is around, does Takeda require qualification on this tool or still exploratory? Qualification means, it goes through the GXP checking in the end.
Didn't actually understand the last part.
He was asking if we've done GXP qualification, and certainly at this stage we haven't.
Okay.
For other tools that we've deployed at Takeda, especially ones that are involved in clinical studies, we've had to do levels of GXP type compliance and validation. At this point, I think the way it's being used is not putting it necessarily into that context. I think if we started reporting certain results, especially safety results, we might have to. For other clients, we've had to do a lot of GXP around pieces of the RWE type tools, just to make sure we can go into scenarios that might overlap clinical.
We've used this purely, we've used this purely in a research capacity, sort of a basic scientific question and hypothesis building capacity, and not a confirmation or certainly not in any sort of clinical trials.
Hi, my question is about the first problem that you chose to solve. I was wondering why you chose that particular question and what the significance is of someone switching their depression medication. I'm assuming there's an implication. I was curious what that is.
Sure, I can speak first to it. I think we all have a little bit of a different perspective. So partly it comes out from a business need. Takeda is in the space of treatment-resistant depression, and we would like to better understand why patients are switching in the hopes of better understanding the etiology of treatment-resistant depression. It could help us prioritize drug targets. We also see the benefit at point of care. It's a lengthy journey for a patient to go from medication to medication to medication to try to find something. And if we can better predict those that don't switch and stay, and what features differ, we might be able to get that patient to the right medication for them faster.
I think I'd say from a commercial standpoint, when you're thinking about treatment switches, a lot of drugs are considered second line or third line drugs, which means first you have to be on drug A, then B, and then you get to the drug that, say, Takeda produces. And to better understand why people are switching, and if there's a specific signature of patients that could benefit from using it much earlier in their treatment pathway, that's commercially beneficial to be able to identify that and educate the physician population that that's a better option for that patient.
And not just the physician population, but also the payers. It's our job to be generating evidence to the payers so that they will reimburse it as a first line or second line. It's healthcare is complicated.
Yeah, I think there's just a broader long-term switch that people are hoping for that's been hard to get to, of this idea of personalized medicine.
Right.
But to get to personalized medicine, you have to know, what are going to be the rules as to when you're going to say, yeah, give this person this whether it's a higher cost or it's a different class of drug first, and make that what is, the standard of practice and protocols and, the whole gamut of how they are processed. Because right now we kind of have one-size-fits-all medicine for a lot of diseases, and that, that doesn't work that well for both the payers saving money or the patients who are going through an experience of bouncing from 3 or 4 drugs that don't work to get to the one that really does.
That makes sense. I had a second question if I'm not taking anyone's time. You mentioned the availability of specific, you called it the data from the insurance companies.
Claims data.
Client data.
Yeah.
And I was wondering if there are similar kind of resources for different kinds of data that could be used for similar applications, not necessarily specifically in pharm, but if there are similar healthcare data resources, data farms, data whatever, for any like lab diagnostics or blood types or anything like that.
Yeah, there's a lot of different sources of data. There's of course electronic health medical records, your EHRs, your EMRs, which is it's similar but quite different than the claims. A lot more things will be documented in it. In claims data, there's some, certainly great strengths of using the data, but some real limitations. Something that isn't reimbursed is typically not coded or is not coded very frequently, so you have a lot of missingness. You also have to be careful with the claims data that someone has that diagnosis, it could be a rule out, so there's real specifics around working with claims data itself, but there's all sorts of like real world data sort of repositories. One of the other ones that I specifically have been working with is patient registries, different patient registries and disease registries. That's a great source of data as well.
Okay, I know I heard a saying about how the cure to cancer is out there, but the data is also segmented. We can't quite get to it. And so that's kind of the heart of the question that I'm asking is I know a lot of that data, you could have it per hospital or, Kaiser might have their own kind of a database, but then if you're not with Kaiser, you can't use it. If there's any kind of a consolidated source for anything similar to these where it seems like it's all of the claims data across all of those segmented components, if there's something similar.
Yeah, so we used here licensed data. So there's a price tag on that. There are sources of data that you as an end user can get, especially with the patient registries. Some of them have been created through the Patient Powered Research Network and the PCORI, if you've heard of that, some of the government initiatives, and you need to put together a proposal as to why you want to use the data, but that tends to be a straightforward process, and so you can get access to data that could be a case control kind of study.
And I was going to say, and to your question, you've heard this about oncology, and there's certainly companies that have put a lot of financial energy towards building those big consolidated data sets. One of them would be like Flatiron, which got acquired by Roche for billions of dollars last year. There's others out there as well. Coda uses sort of a technique to code a bunch of the records and then can make those records available. So there's new startups like Tempest. So you're going to see, especially oncology, there's probably a higher maturity than most other specialized patient populations. More broadly, there's vendors that have put energy in, and one of them is Optum, that has an acquisition they made in a company called Humedica, and another is a company that was called Exploris that was acquired by IBM. And so we've definitely seen these. There's not the same level of consolidation in electronic health records data or other data sets, because unlike the claims world where a lot of the data flows through a small number of clearinghouses, which makes it possible to get a very large integrated set.
Okay.
Most of it's cobbled together by vendors that are doing data licensing and coming up with some kind of transaction with the original groups that have it. And there's a lot more concerns about medical record data because it has more details in it about people's records and their privacy.
Right.
And so there's been a lot of talk about, how do we deal with this? I'd say from our machine learning world, we know we're going to have a very imperfect universe of data, and that's one of the reasons why we're trying to continue to get good at dealing with the data we can have to make the most of it.
Great, thank you.
Well, great. I think we're out of time, but I thank everybody for coming.